Hello, today we look at proof by contraposition. Contraposition is an indirect way of proving the veracity of a conditional statement or implication, usually written as if P then cure and symbolically as P implies cure. The contrapositive of the implication above is if not cure then not P, written symbolically as not cure implies not P. And we have to note the way the contrapositive is obtained from its implication, in that usually we switch the positions of the premise and the conclusion and then negate both sides. So as you can see, the implication is P implies cure, but the contrapositive is not cure implies not P. So the left hand side has been switched over to the right hand side, while the right hand side is switched over to the left hand side. Both sides are then negated before we obtain the contrapositive. This procedure is very important for you to be able to determine the contrapositive when you are doing your proof, because if you get the contrapositive wrongly, of course your proof wouldn't work. The next important thing that we need to know, in fact, it is the principle behind the proof by contraposition, is the fact that an implication and its contrapositive are always logically equivalent. We can write that symbolically as P implies cure is logically equivalent to not cure implies not P. So we note then that when two statements are logically equivalent, it simply means they are different ways of expressing the same thing. We can further make an illustration to get the concept clearly by looking at an example. Take the case of a statement P which says Peter does not work hard, and then another statement Q, Peter is intelligent. The negation of P is not P. When you negate an already negated statement, you now have a positive statement. Hence, the negation of Peter does not work hard should be Peter works hard, while the negation of Peter is intelligent should be Peter is not intelligent. A situation might arise in which a student, Peter, is always passing his exams. Then somebody looks at his status and makes an observation whereby he says, if Peter does not work hard, then he is intelligent. He is referring to the fact that Peter is always passing his exams, and so his observation is that if Peter does not work hard, then he is intelligent, because most of the time, everything being equal, students who are always successful in school is either they are intelligent or they work hard. Another observer, independent of the first, may also look at the status of Peter always passing his exams, but instead make another statement which is very identical to the first, by instead saying if Peter is not intelligent, then he works hard. And clearly we can see that these two statements are all saying the same thing, although in different ways, because they all refer to the fact that Peter always passes his exams either because he works hard or because he is intelligent. Now we can further make a demonstration to show that the two statements, the implication and the contrapositive, are always logically equivalent. That means they always refer to the same thing, although in different ways of expressing it. By looking at a truth table, all the possibilities of combining the premise and the conclusion in all the different statements to arrive the fact that P implies cure gives the results of the truth table, which are the same or identical to those of not P implies not P. And clearly from the truth table, it shows that P implies cure and not cure implies not P are logically equivalent. From the above illustrations, it is then clear that if we want to prove that a conditional statement is true, we may instead find it convenient to do so by indirectly proving that its contrapositive is true, usually by some direct method. In the cases where contraposition has to be used in mathematical proofs, it will be either the examiner imposes it to you, or by observation you notice, especially a conditional statement, that the direct method will be difficult to go by, then convert that implication into its contrapositive, and you might see that it is now easy to prove by the contrapositive using the direct method. Now the direct method works in such a way that you start by assuming not Q and then proceeding with arguments together with existing established mathematical concepts in order to arrive not P. We'll proceed to have examples, and the first example we'll be looking at is proof by contraposition that for any integer n, if n squared is even, then n is even. Since the question is talking about the parity of integers, it is good for us to start by looking at the algebraic expressions for integers that are even and those that are odd. If you have an integer k, then 2k will always be even and 2k plus 1 will always be odd. Now we start our proof straight away by looking again at the statement that we are supposed to prove. If n squared is even, then n is even. This clearly is very difficult for us to start with n squared being even and arrive n being even by a direct method. So we instead take the contrapositive, which would be if n is not even, then n squared is not even. Notice how the conclusion and the premise have been exchanged in the contrapositive and then negated. We can also express the contrapositive as if n is odd, then n squared is odd, because the negation of even is odd. We now start our direct proof of the contrapositive by supposing that n is odd and then expressing n algebraically as an odd number, whereby we say n equals 2k plus 1 for some integer k. We proceed now to verify the parity of n squared by putting 2k plus 1, the algebraic expression of n, and squaring it, which would give 4k squared plus 4k plus 1. And in the first two terms we can factorize 2 to have 2 into 2k squared plus 2k plus 1. As you can notice, the parity of n squared is already indicating some oddness there, but we can make it clear by letting t, another integer, to be 2k squared plus 2k, the bracket in that expression, whereby we will now see that n squared equals 2t plus 1, which is clearly an odd integer. We can then conclude that since it is true that if n is odd, then n squared is odd, the proposition if n squared is even, then n is even is true by contraposition. We move over to the second example, prove by contraposition that for any integers x and y, if xy is even, then x is even or y is even. We note that the conclusion in this implication is a compound statement, and so we have to be very careful when arriving its negation as we are writing down the contrapositive. In fact, when doing your contraposition and there are compound statements, usually statements having the or the and, you are supposed to use the Morgan's laws in arriving their negations. So let us look at the statement again. The proposition is if xy is even, then x is even or y is even. So the contrapositive should then be if x is odd and y is odd, then xy is odd. Now the premise of the proposition was xy is even, so the conclusion of the contrapositive will then be its negation, which is xy is odd. while the conclusion of the implication was x is even or y is even, so that it's the premise of the contrapositive, which is supposed to be its negation, would then be x is odd and y is odd, which is obtained actually from one of De Morgan's laws. That law states that not P or Q is logically equivalent to not P and not Q. This can be proven also using truth tables, but we can clearly see that the negation of P or Q is logically equivalent to not P and not Q. That is why the negation of x is even or y is even is x is odd and y is odd. So we proceed with our proof then by supposing that x is odd and y is odd. Then we define them algebraically as odd numbers, x equal to k plus 1 and y equals to t plus 1 for some integers k and t. Then from there we proceed to verify the parity of xy by multiplying their algebraic forms. 2k plus 1 into 2t plus 1 would give 4kt plus 2k plus 2t plus 1, which clearly, if we factorize 2 in the first three terms of the expansion, we would get 2 into 2kt plus k plus t plus 1, and we can observe already the parity of that statement, which shows that it is odd. But to make it clear, we can let 2kt plus k plus t to be another integer, so that xy now becomes 2m plus 1, which clearly shows that xy is odd. Since we have successfully proven that if x is odd and y is odd, then xy is odd, which is the contrapositive of the statement we originally set out to prove, then we can conclude by saying that since it is true that if x is odd and y is odd, then xy is odd, the proposition if xy is even, then x is even or y is even is true by contraposition. Another example, prove by contraposition that if a does not divide b, then a does not divide c, or a is not equal to b plus c. Now we write the proposition again, and then we carefully write down its contrapositive. In writing the contrapositive, the premise of the implication should be negated and then written as the conclusion. So a does not divide b is negated to have a divides b. The negation of the conclusion in the implication will now become the premise of the contrapositive. And to have the negation, we again have to rely on De Morgan's law, whereby we negate a does not divide c to have a divides c, then change the or to and then negate a is not equal to b plus c to have a is equal to b plus c. From there we can then proceed with the direct proof. Suppose a divides c and a is equal to b plus c. Then for some integer k, c would be equal to ka. Remember, a divides c simply means a is a factor of c, which can also mean that c is a multiple of a, and clearly that is what we have written. We can then proceed to replace c in the equation a equals b plus c to have a equals b plus ka, and if you make b the subject, you would have b equals 1 minus k into a, and this clearly shows that b is a multiple of a, or that a divides b. And so we have successfully proven that if a divides c and a is equal to b plus c, then a divides b by a direct method. Our conclusion will then be that since it is true that if a divides c and a is equal to b plus c, then a divides b, then the proposition if a does not divide b, then a does not divide c, or a is not equal to b plus c is true by contraposition. finally, I would end by leaving you with an exercise to test your knowledge. Prove by contraposition that if x plus y is less than 15, where x and y are real numbers, then x is less than 8 or y is less than 8. A hint, you note that the negation of x plus y is less than 15 should be x plus y is greater than or equal to 15. The same thing applies to the negations of x less than 8 and y less than 8.